The universe is a place of infinite wonder, where every discovery seems to peel back another layer of mystery, only to reveal something even more baffling beneath. Think about the last time you looked up at the night sky, feeling that quiet awe as the stars blinked back at you. Now, imagine witnessing something up there that shouldn't exist. A flash of light where none was predicted, a signal repeating from the void with no discernible source, or a celestial object moving in ways that defy the laws of physics. These aren't just plot twists from a sci-fi movie. They're real, documented events that have left astronomers scratching their heads for decades. What if I told you that some of the most brilliant minds on Earth, armed with cutting-edge technology, still can't explain what's happening right above our heads? From mysterious radio bursts that pulse like a cosmic heartbeat to galaxies that spin in ways that shouldn't be possible, the cosmos is teeming with enigmas that challenge everything we think we know. These aren't just minor curiosities, they're gaping holes in our understanding of the universe, reminding us that for all our progress, we've barely begun to unravel its secrets. That's exactly what we're diving into today, 20 of the most jaw-dropping, spine-tingling cosmic mysteries that continue to stump scientists. Some of these events might sound like they're straight out of a Twilight Zone episode, but trust me, they're very real. And by the time we're done, you'll see why these puzzles aren't just fascinating. They're clues that could rewrite the textbooks of astronomy. So buckle up, because we're about to take a journey into the unknown, where the rules of reality seem to bend, and the universe keeps its most astonishing secrets just out of reach. Ready to explore? Let's begin. The WOW signal remains one of the most electrifying mysteries in the history of astronomy, a fleeting whisper from the cosmos that still echoes in the minds of scientists today. It all began on a quiet August night in 1977, when a radio telescope in Ohio picked up something extraordinary, a burst of radio waves so powerful it shot off the charts. For 72 heart-pounding seconds, the signal blazed across a narrow frequency band, a frequency scientists had long considered ideal for interstellar communication. Then, just as suddenly as it appeared, it vanished, never to be heard again. What made this signal so extraordinary wasn't just its strength, but its precision. Natural cosmic phenomena like pulsars or quasars usually scatter their energy across a wide range of frequencies, but the WOW signal was laser-focused, as if someone had tuned a cosmic radio to one exact station. The astronomer who discovered it, Jerry Amon, was so stunned he circled the data printout in red ink and scribbled "WOW" in the margin, a name that stuck. Decades later, we still don't know what caused it. Was it a passing comet reflecting sunlight in just the right way, a glitch in the telescope, or, as some daringly speculate, could it have been a deliberate transmission from another civilization? The debate rages on because the signal checks so many boxes for what scientists theorize an alien broadcast might look like. Yet without a repeat detection, it's impossible to confirm. Projects like SETI have scanned the same patch of sky thousands of times, hoping for another clue, but silence reigns. Some argue it was a one-in-a-million natural event we simply don't understand yet. Others counter that nature rarely produces such a clean, artificial-looking signal. One thing's certain, the WOW signal is a haunting reminder that the universe might be shouting at us, and we're still learning how to listen. Fast radio bursts are like the universe playing a cosmic game of Morse code, except we haven't cracked the cipher yet. Picture this: in less time than it takes to blink, a burst of radio waves shoots across billions of light years, packing more energy than the sun emits in days. These fleeting signals, lasting mere milliseconds, were first discovered in 2007, and they've been baffling scientists ever since. What makes them even stranger is their unpredictability. Some burst once and vanish without a trace, while others, like the famous repeater FRB 1212, send out signals in a pattern that defies easy explanation. The leading theories point to extreme celestial objects magnetars, for instance, which are neutron stars with magnetic fields so intense they could strip the information from a credit card halfway across the galaxy. When these magnetars experience starquakes or magnetic flares, they might unleash these colossal bursts. But here's the twist: not all fast radio bursts fit this mold. Some come from regions of space with no obvious source, and their brightness suggests a mechanism far more energetic than anything we've observed before. Could it be colliding black holes, or something even more exotic, like cosmic strings, theoretical defects in the fabric of spacetime itself? Then there's the elephant in the room, the possibility, however slim, that these bursts aren't natural at all. The repeating patterns in some FRBs have fueled speculation about artificial origins, perhaps a beacon from an advanced civilization, or even a byproduct of alien technology harnessing unimaginable power. While most astronomers lean toward natural explanations, the sheer mystery of these signals keeps the door open to wilder ideas. Every new detection adds another piece to the puzzle, but the full picture remains frustratingly out of reach. What's truly remarkable is how these bursts serve as cosmic breadcrumbs, leading us deeper into the unknown. By studying the way their radio waves disperse as they travel through space, scientists have even used FRBs to map the invisible matter between galaxies, turning a mystery into a tool for discovery. Yet the central question lingers: what cosmic powerhouse could possibly produce these fleeting, universe-spanning flashes? Until we catch one in the act or uncover a smoking gun source, fast radio bursts will remain one of the most tantalizing enigmas in modern astronomy. Tabby's star doesn't just flicker, it behaves like a cosmic light switch with a mind of its own. Officially catalogued as KIC 8462852, this unassuming star in the constellation Cygnus has baffled astronomers since its discovery in 2015. Unlike typical stars whose brightness dips in regular, predictable patterns when planets pass in front, Tabby's star dims erratically, sometimes by as much as 22%, a staggering drop that defies conventional explanation. Imagine if the sun suddenly lost a fifth of its brightness for days or weeks with no obvious cause. That's the level of mystery we're dealing with here. At first, scientists thought a swarm of comets might be responsible, their dusty tails blotting out the star's light. But comets couldn't account for the sheer scale of the dimming or the irregular timing. Another theory suggested vast clouds of interstellar dust, yet the star's light doesn't scatter the way dust typically would. Then came the most provocative idea of all: alien megastructures. The notion, first floated by astronomer Jason Wright, proposed that an advanced civilization might have built a Dyson swarm, a massive array of energy-collecting satellites encircling the star. While captivating, even Wright admitted it was a last resort hypothesis. Still, the idea captured the public's imagination, turning Tabby's star into a cultural phenomenon. Years of intense study have only deepened the puzzle. Observations from ground-based telescopes and space observatories like Kepler and Hubble have ruled out some possibilities while raising new questions. Some dips in brightness last for days, others for weeks, with no discernible pattern. Even stranger, historical data suggests the star's overall luminosity has been gradually fading for over a century, a trend unmatched by any known stellar behavior. Could it be an undiscovered natural phenomenon, like a colossal collision of planets or a never-before-seen type of stellar activity? The truth is, Tabby's star challenges our understanding of how stars and their surroundings evolve. Every new observation seems to muddy the waters further, leaving astronomers with more questions than answers. What's clear is that this star is doing something extraordinary, something that doesn't fit neatly into any existing cosmic playbook. Whether the explanation turns out to be mundane or revolutionary, Tabby's star reminds us that the universe still holds surprises capable of rewriting the rules. And until we solve its riddle, it stands as a beacon of the unknown, daring us to look deeper. The dark flow is like a cosmic river tugging entire galaxies off course, and no one knows what's creating the current. Picture the universe expanding, with galaxies drifting apart like dots on an inflating balloon. That's the expected pattern, but in 2008, astronomers noticed something bizarre. Hundreds of galaxy clusters weren't just moving outward, they were racing in the same direction at breakneck speeds, as if pulled by some invisible hand. This wasn't just a slight deviation. These clusters were hurtling at over 2 million miles per hour toward a mysterious region of space beyond the edge of our observable universe. What could possibly exert such a staggering gravitational pull? One theory suggests a massive concentration of matter, perhaps a supercluster of galaxies so enormous it warps space-time on an unimaginable scale. But here's the catch. According to our current models, the universe should be relatively uniform at such vast distances. There shouldn't be anything large enough outside our cosmic horizon to cause this kind of motion. That's why some scientists speculate the dark flow might be evidence of another universe brushing against ours, its gravity leaking through like a shadow from beyond the veil. Others argue the answer lies closer to home. Could flaws in our measurements or gaps in the standard model of cosmology explain this anomaly? After all, dark flow challenges two pillars of modern astronomy: the cosmological principle, which states the universe should look roughly the same in all directions, and the idea that dark energy drives uniform expansion. If the dark flow is real, it implies there's structure and asymmetry on scales we never anticipated. Yet every attempt to dismiss it as an observational error has hit a wall. The signal persists across multiple studies, and the statistical odds of it being a fluke are astronomically low. Even the Planck satellite, which mapped the cosmic microwave background with unprecedented precision, couldn't resolve the mystery. Some researchers propose exotic solutions, like cosmic defects left over from the Big Bang or gravitational echoes from a pre-Big Bang era. But until we can peer beyond the cosmic horizon or detect the hidden mass responsible, the dark flow remains one of cosmology's most profound enigmas. A silent reminder that the universe might be far stranger and far larger than we ever imagined. The Great Attractor lurks in the cosmic shadows like a phantom tugging at the strings of our galaxy, and we can't even see what it is. Imagine a force so powerful it's dragging the Milky Way and thousands of other galaxies toward it at over 1 million miles per hour, yet it's hidden behind a thick curtain of interstellar dust and stars in our own backyard. This gravitational enigma, sitting about 250 million light-years away in the direction of the constellation Centaurus, has been pulling us toward it for decades, and we're still no closer to understanding its true identity. At first, astronomers thought it might be a colossal cluster of galaxies, their combined gravity creating this immense pull. But when they mapped the region, the numbers didn't add up. The visible matter there, the galaxies we can see, simply isn't enough to account for the staggering force at work. That's when the theories got interesting. Some suggest the Great Attractor could be part of something even larger, the Laniakea supercluster, a vast cosmic web of galaxies spanning 500 million light-years, with the attractor acting as its gravitational heart. Others wonder if dark matter, that invisible glue holding the universe together, might be clumped there in unprecedented densities, magnifying its pull beyond what normal matter could achieve. But here's where it gets even stranger. The Great Attractor isn't the end of the mystery. It might just be a waypoint. Beyond it lies the Shapley supercluster, an even more massive collection of galaxies that could be the true source of this cosmic tide. Yet the farther we look, the more questions arise. Why do galaxies flow toward these regions with such precision? Could there be structures in the universe so immense they redefine our understanding of cosmic scales? The irony is palpable. We're being pulled toward something we're struggling to observe directly. The Milky Way's own disk blocks our view, soaking up light and radio waves like a cosmic fog. It's only with infrared and X-ray telescopes that we've begun piecing together glimpses of what lies behind the veil. Each new observation chips away at the mystery, revealing filaments of galaxies and hints of unseen mass, but the full picture stays frustratingly out of focus. What makes the Great Attractor so compelling isn't just its hidden nature. It's the reminder that even as we map the cosmos, we're still missing huge pieces of the puzzle. Whether it's a supercluster, a dark matter anomaly, or a signpost to something even grander, this gravitational giant challenges us to rethink how the universe organizes itself on the largest scales. And until we find a way to see through the galactic blind spot hiding it, the Great Attractor will keep pulling us not just through space, but deeper into the unknown. Oumuamua wasn't just another space rock, it was a visitor from another star system, and it behaved like nothing we'd ever seen before. When this mysterious object streaked through our solar system in 2017, astronomers scrambled to study it, only to find it defied every expectation. First, there was its shape, long and cigar-like, stretching perhaps a quarter-mile in length, but only a tenth as wide. Most asteroids or comets are lumpy or spherical, but Oumuamua's elongated form was bizarre enough to spark instant fascination. Then came the real shocker. It wasn't just coasting on gravity's pull. As it rounded the sun, it sped up slightly, as if pushed by an unseen force. At first, scientists assumed it was a comet venting gas as it warmed, a natural explanation for the extra kick. But telescopes detected no telltale coma or tail, the usual signs of outgassing. That left researchers scratching their heads. Could sunlight alone, bouncing off its surface, have provided enough pressure to nudge it faster? The math barely worked, and the lack of visible debris made the theory feel like a stretch. That's when the speculation took a wilder turn. Harvard astronomer Avi Loeb famously suggested Oumuamua might be artificial, a solar sail or probe from an advanced civilization, its thin shape perfect for riding light waves across the galaxy. The idea made headlines, but most astronomers remained skeptical. After all, extraordinary claims require extraordinary evidence, and Oumuamua was already racing away, too distant for follow-up observations. The truth is, we may never know what this interstellar traveler really was. By the time we spotted it, Oumuamua was already leaving, and our window to study it slammed shut. Some argue it was a fragment of a shattered planet, ejected from another star system eons ago. Others propose it's a new type of dark comet, rich in organic molecules that don't vaporize the way typical comet ice does. There's even a chance it's a piece of nitrogen ice sheared off a Pluto-like exoplanet, a cosmic iceberg tumbling through the void. What makes Oumuamua so haunting isn't just its strangeness, but the tantalizing possibilities it represents. It's proof that interstellar objects pass through our neighborhood more often than we thought. We just hadn't been looking closely enough. Since its discovery, telescopes like Pan-STARRS have been tuned to spot more of these visitors, and already a second one named Borisov has been detected. But unlike Borisov, which clearly resembled a comet, Oumuamua remains in a class of its own. Was it a natural oddity or something more? Without another look, the debate may never settle. One thing's certain, this cosmic interloper reminded us that the universe is full of surprises, and some of them might be sailing right past us, silent and enigmatic, before we even have time to wonder. The Fermi Paradox cuts to the heart of our cosmic loneliness, a puzzle so profound it reshapes how we see our place in the universe. On paper, the numbers seem undeniable. With hundreds of billions of stars in our galaxy alone, many hosting planets in the so-called Goldilocks zone where liquid water could exist, the universe should be buzzing with life. Even if only a tiny fraction of those worlds developed intelligent civilizations, the Milky Way ought to host thousands of them, some far older and more advanced than ours. So where is everybody? This glaring contradiction between expectation and reality is the essence of the Fermi Paradox, named after physicist Enrico Fermi, who famously posed the question during a casual lunchtime conversation in 1950. If they exist, why haven't we seen them? Possible explanations range from sobering to spine-chilling. One camp argues that life might be extraordinarily rare, that Earth is a cosmic fluke, a perfect storm of conditions unlikely to repeat. Others suggest that intelligent civilizations inevitably hit a great filter, a catastrophic barrier, whether nuclear war, environmental collapse, or runaway AI, that prevents them from reaching interstellar travel. If true, this filter could lie ahead of us, a silent warning etched into the stars. Then there's the eerie possibility that advanced civilizations are out there, but they're deliberately avoiding us. Imagine a galactic zoo hypothesis where Earth is quarantined like an exhibit, or a dark forest theory where civilizations stay hidden to avoid attracting predators. Technology adds another layer to the mystery. We've been listening for alien radio signals for decades with projects like SETI, yet the silence is deafening. Perhaps they communicate in ways we can't detect using neutrino beams or quantum entanglement. Or maybe they've moved beyond physical forms, existing as digital consciousness in vast supercomputers. There's even a chance we're looking in the wrong places. The universe is unimaginably vast. Signals could be passing through our solar system like whispers in a hurricane, too faint or too brief for our instruments to catch. What makes the Fermi Paradox so unsettling isn't just the lack of answers, it's the humbling realization that we might be asking the wrong questions. Our assumptions about what life should look like or how civilizations ought to behave could be hopelessly anthropocentric. After all, a species millions of years ahead of us might operate on scales and timelines we can't begin to fathom. Until we find definitive proof, whether a signal, an artifact, or even an encounter, the paradox remains a mirror, reflecting back our deepest hopes and fears about life's place in the cosmos. And in that silence, the universe seems to whisper a challenge: keep searching. The Black Knight satellite is the stuff of conspiracy legends, a shadowy object orbiting Earth that some claim has been watching us for thousands of years. Stories about this enigmatic presence date back to the late 1950s, when amateur radio operators reported picking up strange, delayed echoes of their own transmissions, as if something in space was bouncing signals back. Then came the grainy photographs, black and white images from early space missions that appeared to show a dark, irregularly shaped object drifting against the backdrop of our planet. To believers, this wasn't just space junk, it was evidence of an ancient extraterrestrial probe, silently monitoring humanity's progress from the heavens. Scientists have a far simpler explanation: orbital debris. The early days of space exploration left countless fragments floating in Earth's orbit, discarded rocket parts, defunct satellites, even lost tools from astronaut missions. The Black Knight, they argue, is likely just one of these forgotten relics, its odd shape the result of twisted metal or solar panels catching the light at unusual angles. But here's where the mystery thickens. Some images, like the one captured during a 1998 Space Shuttle Endeavour mission, show an object with sharp edges and symmetry that doesn't quite match the chaotic profile of typical debris. Could it be a classified satellite or something more exotic? The legend gained traction when enthusiasts pointed to a supposed 12,000-year-old Sumerian text describing a star that never moves, interpreted by some as a reference to the Black Knight. Skeptics dismiss this as cherry-picked mythology, but the allure persists. Even famed inventor Nikola Tesla claimed in 1928 to have intercepted mysterious radio signals he believed originated from beyond Earth. Decades later, similar claims would resurface, tying Tesla's experience to the Black Knight narrative. Modern astronomy hasn't helped settle the debate. While most experts agree the object is likely a thermal blanket lost during a spacewalk or a fragment from an old satellite, no one has definitively identified it. The lack of concrete answers fuels speculation, turning the Black Knight into a Rorschach test for our fascination with the unknown. Is it a relic of human spaceflight, a piece of interstellar archaeology, or just a cosmic mirage? Until someone retrieves it or it vanishes back into the void, the legend will keep orbiting right alongside it, a ghost story written in the stars. The Pioneer Anomaly is one of those quiet cosmic puzzles that refuses to fade into obscurity, a subtle but persistent whisper from the depths of space that challenges our understanding of physics itself. When NASA Pioneer 10 and 11 spacecraft ventured beyond the asteroid belt in the 1970s and 80s, they carried humanity's hopes into the unknown. But as they raced toward the outer solar system, something peculiar happened. Both probes began slowing down ever so slightly, as if an invisible hand were gently tugging them back toward the sun. This deceleration was tiny, about a billionth of the force we feel from Earth's gravity, but it was consistent, unexplainable, and utterly unexpected. At first, scientists assumed it was a glitch. Maybe residual heat from the spacecraft's plutonium power sources was leaking unevenly, creating a faint but measurable push. Or perhaps the way we tracked the probes using Doppler shifts in their radio signals had some hidden flaw. But after years of painstaking analysis, the anomaly stubbornly remained. Even after accounting for thermal effects and refining measurement techniques, Pioneer 10 and 11 kept decelerating at a rate that defied conventional physics. The discrepancy was small enough to dismiss as noise in most contexts, but in the precise world of deep space navigation, it stood out like a sore thumb. This wasn't just a technical curiosity. The Pioneer Anomaly hinted at something far more profound, the possibility that our equations of gravity might be incomplete. Einstein's theory of general relativity has held up spectacularly well for over a century, but what if, under certain conditions, it needed tweaking? Some theorists proposed modifications to gravity itself, suggesting unseen dimensions or exotic dark matter interactions could be at play. Others wondered if the answer lay closer to home, an overlooked quirk in how spacecraft dissipate heat or reflect radiation. Then, in 2012, the mystery took an unexpected turn. A team of researchers meticulously reconstructed the probe's thermal emissions and found that, when modeled with extreme precision, the heat from their power systems could explain most of the anomaly. Case closed, not quite. While the thermal explanation satisfied many, a vocal minority of scientists argue the numbers don't add up perfectly. There's still a faint residual effect, a ghost in the data, that lingers unexplained. What makes the Pioneer Anomaly so compelling isn't just the scientific debate it sparked, but the humility it imposed. Here were two human-made objects, hurled into the void with the best technology of their era, revealing a gap in our knowledge so subtle we might have missed it entirely. Whether the final answer lies in thermal physics, unseen forces, or something even more revolutionary, the anomaly serves as a reminder. Even in the vastness of space, the smallest deviations can point to the biggest questions. And sometimes the universe teaches us not with a shout but with a whisper. The Zodiacal Light is one of those celestial mysteries that's easy to miss but impossible to forget once you've seen it. Imagine standing under a perfectly dark sky just before dawn or after sunset, when the horizon is free of city glare, and spotting a faint, ethereal glow stretching upward like a tilted cone of hazy light. This isn't the Milky Way or a stray comet, it's sunlight, scattered by countless tiny dust particles floating in the inner solar system. For centuries, astronomers assumed this dust was simply debris left behind by comets or asteroid collisions. But the more we study it, the less that explanation holds up. The puzzle begins with the dust itself. If it came from comets, we'd expect it to follow their orbits, clustering along their paths like breadcrumbs. Instead, the Zodiacal Light's particles are spread far more evenly, almost as if someone sprinkled them deliberately across the solar system's plane. Even stranger, the dust grains are far smaller and more uniform than typical comet debris, some no larger than smoke particles. Where did they come from? One theory points to Mars, where dust storms might launch particles into space, but the sheer volume needed to sustain the glow makes this unlikely. Others suggest a slow, steady grinding of asteroids over eons, yet that doesn't account for the dust's peculiar distribution. Then there's the light's behavior. Unlike predictable astronomical events, the Zodiacal Light shifts in intensity and shape, sometimes appearing brighter or more structured than expected. In the 1990s, spacecraft even detected strange dust bands orbiting the Sun, perfectly aligned with the zodiacal glow but with no clear source. Could there be undiscovered asteroids or extinct comets feeding this cosmic dust reservoir? Or is something more exotic at work, like interstellar dust drifting into our solar system and becoming trapped by the Sun's gravity? The most tantalizing clue came in 2020, when NASA's Juno mission made an unexpected discovery. As the spacecraft journeyed to Jupiter, its star tracking cameras picked up far more dust impacts than predicted particles that shouldn't have been there if the Zodiacal Light source was local. Some scientists now wonder if this dust isn't from our solar system at all, but a remnant of the primordial cloud that formed the planets billions of years ago, lingering like a ghost in the cosmic attic. What makes the Zodiacal Light so captivating isn't just its beauty, but what it represents, a cosmic crime scene with no obvious culprit. Every speck of dust holds a clue, but the bigger picture stays frustratingly out of focus. Whether it's the fingerprint of a long-lost comet swarm, the echo of a violent planetary collision, or something entirely unforeseen, this gentle glow reminds us that even the emptiest corners of space are teeming with unanswered questions. And until we solve them, the Zodiacal Light will keep shining, a silent enigma written in scattered sunlight. The missing Baryon problem is like a cosmic accounting error, one where the numbers just refuse to add up, no matter how many times we check the math. Picture the universe's matter as a vast ledger. On one side, we've mapped the stars, galaxies, and gas clouds we can see. On the other, sophisticated simulations predict how much normal matter, called baryonic matter, should exist based on the Big Bang's afterglow. But when we tally the two columns, something shocking emerges. Nearly half of the universe's expected baryons are missing. Not dark matter, not some exotic particle, but the ordinary protons and neutrons that make up everything from planets to people. So where did it all go? For decades, scientists assumed this missing matter was simply hiding in plain sight. perhaps too diffuse or cold to detect with our telescopes. One leading theory points to the cosmic web, those vast, thread-like filaments of gas stretching between galaxies, theorized to contain enough warm, hot intergalactic medium WIM to solve the puzzle. The catch: this gas is so thinly spread and scorching hot millions of degrees that it emits almost no visible light. Instead, it betrays its presence only when backlit by distant quasars, their light absorbed in telltale wavelengths as it passes through these invisible rivers of matter. Even then, the detections account for only a fraction of the deficit. Then there's the role of black holes. Some researchers suggest supermassive black holes at galactic centers might be acting like cosmic furnaces, ejecting baryons into intergalactic space at speeds too high for current instruments to track. Others propose the missing matter could be locked in rogue planets or failed stars drifting unseen between galaxies. But these ideas, while creative, struggle to explain the sheer scale of the discrepancy. The truth is, we're not just missing a few scattered atoms, we're searching for an amount equivalent to all the visible matter in the universe, twice over. Recent breakthroughs hint at progress. X-ray telescopes like ESA's XMM Newton have begun spotting faint glows from the WIM, while advanced simulations suggest much of the missing matter might reside in low-density regions previously dismissed as empty. Yet every new discovery seems to deepen the mystery. Why is this baryon hunt so difficult? Part of the challenge lies in the universe's sheer size. The missing matter isn't concentrated in one place. It's smeared across billions of light years, a cosmic needle in a haystack scenario where the haystack is the entire observable universe. What makes this puzzle so gripping isn't just the scientific stakes, it's the humbling reminder of how much we still don't understand about the cosmos. If we can't even account for the ordinary matter, how confidently can we model the universe's past or future? The hunt continues, with next-generation telescopes and space missions poised to scan deeper and fainter than ever before. Until then, the missing baryons stand as a silent testament to the gaps in our cosmic ledger, gaps that might one day rewrite our understanding of where and what the universe is truly made of. The axis of evil isn't just a dramatic name. It's a cosmic curveball that threatens to upend one of astronomy's most cherished principles. Imagine mapping the faint afterglow of the Big Bang, the cosmic microwave background, expecting to see a random, isotropic universe, only to discover an eerie alignment stretching across the sky like a phantom fingerprint. That's exactly what scientists stumbled upon in 2004 when data from NASA's Wilkinson Microwave Anisotropy probe revealed something unsettling. The hot and cold spots in this primordial light weren't distributed as randomly as they should be. Instead, they seemed to line up along a specific axis, as if the early universe had a preferred direction. This discovery flies in the face of the cosmological principle, the bedrock idea that the universe should look roughly the same in all directions on large scales. No matter where you stand in the cosmos, the laws of physics and the distribution of matter should appear uniform. But the axis of evil, named half-jokingly for its defiance of this principle, suggests otherwise. Some researchers argue it's just a statistical fluke, a cosmic illusion caused by the way we're interpreting the data. After all, the universe is vast, and even random distributions can sometimes appear patterned to the human eye. But the odds of this alignment happening by chance are slim, around 1 in 10,000, making it harder to dismiss as mere coincidence. Deeper analysis only deepened the mystery. When the European Space Agency's Planck satellite mapped the cosmic microwave background with even higher precision in 2013, the axis persisted. Not only that, but the alignment seemed to connect to other puzzling features, like an unexplained cold spot in the southern sky and a curious asymmetry in the universe's expansion rate. Could these all be threads of the same cosmic tapestry? Theories range from the mind bending to the revolutionary. Some propose the axis is a remnant of pre-Big Bang physics, a scar from a collision with another universe in the multiverse. Others suggest it's evidence of a primordial magnetic field that shaped the early cosmos in ways we don't yet understand. Then there's the unsettling possibility that we're seeing the shadow of something beyond our observable universe. If a supermassive structure lies just past the cosmic horizon, its gravitational pull could theoretically warp the microwave background, creating the illusion of an axis. But this raises even thornier questions. What kind of structure could exert such influence, and why would it exist in the first place? The axis of evil doesn't just challenge our models, it forces us to confront how little we know about the universe's true scale and structure. What makes this anomaly so compelling isn't just its defiance of expectations, but the way it exposes the limits of our cosmic perspective. Like a ship navigating by stars we've only just begun to map, we're left wondering if the universe is far stranger and far more intricate than our theories have dared to imagine. Until we unravel this alignment's true nature, it stands as a silent challenge to the very foundations of cosmology, a reminder that the universe, even in its infancy, might have been playing by rules we're only starting to glimpse. The Boötes Void isn't just empty, it's a cosmic desert so vast it feels like the universe forgot to fill in a piece of itself. Stretching 330 million light-years across, this staggering region of space holds only a handful of galaxies where thousands should exist. To put that in perspective, if the Milky Way were a single grain of sand, the Boötes Void would be an empty football stadium with just a few scattered grains lost in the bleachers. Astronomers first stumbled upon this eerie emptiness in the 1980s, and decades later, its existence still defies every expectation of how matter should be distributed in the cosmos. What makes the Boötes Void so unsettling isn't just its size, but the way it upends our understanding of cosmic structure. The universe, at its largest scales, is supposed to resemble an intricate web filaments of galaxies woven around vast bubbles of empty space. But even in that framework, voids this colossal shouldn't exist. Simulations of the cosmos predict much smaller gaps, with galaxies clustering like foam on the surface of a turbulent sea. The Boötes Void, by contrast, is more like a bottomless trench. So how did it form? One theory suggests it's the result of countless smaller voids merging over billions of years, like soap bubbles combining into one gigantic cavity. But even that explanation struggles to account for the sheer scale of the emptiness. Then there's the darker possibility. What if the void isn't empty at all? Some researchers speculate it could be packed with invisible matter, dark matter so exotic it doesn't interact with light or normal matter in any way we can detect. Others wonder if it's evidence of a cosmic collision, a scar left behind when our universe brushed against another in the multiverse, sucking galaxies out like a gravitational vacuum. Even more radical is the idea that the void might be home to a super-civilization that somehow harnessed the energy of entire galaxies, leaving behind a ghostly footprint. But perhaps the most humbling explanation is also the simplest. We're seeing a statistical fluke on a scale we can barely comprehend. The universe is unimaginably large, and even the unlikeliest arrangements of matter, or lack thereof, might occasionally appear. Yet the longer we study the Boötes Void, the less that answer satisfies. The few galaxies that do reside there seem oddly clustered along its edges, as if huddling together for safety. Some even exhibit strange motions, as though they're being pulled toward something unseen in the void's depths. The mystery deepens when you consider light from distant quasars passing through the void. Normally, this light would dim slightly as it interacts with sparse intergalactic gas, but observations show less attenuation than expected, almost as if the void isn't just empty of galaxies, but of the diffuse gas that should linger between them. It's as if someone took a cosmic eraser and scrubbed the region clean. Whether it's a natural anomaly, a sign of physics beyond our grasp, or something even more extraordinary, the Boötes Void stands as a silent challenge to our models of the cosmos. It reminds us that for all our telescopes and supercomputers, the universe still holds pockets of profound mystery, places where the rules as we know them seem to dissolve into darkness. And until we can peer deeper into that emptiness, it will remain one of astronomy's most haunting puzzles. The Red Rectangle Nebula doesn't just stand out in the cosmos, it practically defies it. While most nebulae swirl and twist in chaotic, organic shapes, this enigmatic structure near the constellation Monoceros looks like it was drafted with a cosmic ruler. Its stark, geometric form, two intersecting cones of glowing gas forming an almost perfect X-shape, is so precise that it feels artificial, as if someone etched it into the fabric of space. But this isn't the work of alien architects. It's a natural phenomenon that's baffled astronomers since its discovery in the 1970s. At the heart of the nebula lies a dying binary star system, HD 44179, whose stellar winds and radiation should be blowing gas and dust outward in all directions. So why isn't the nebula a messy, spherical shell like so many others? The leading theory points to an extraordinary circumstellar disk, a dense ring of dust and debris orbiting the stars like a hula hoop tilted edge onto Earth. As material gets ejected from the stars, this disk funnels it into two opposing cones, creating the nebula's signature hourglass shape. But here's the twist. Disks around stars aren't uncommon, yet none sculpt their surroundings with such razor-sharp symmetry. Something about this system, perhaps the star's orbits, the disk's composition, or even unseen magnetic fields, is acting like a cosmic stencil, forcing the outflow into those crisp, angular lines. Then there's the color. The red rectangle's eerie glow comes from a type of organic molecule called polycyclic aromatic hydrocarbons, which fluoresce under starlight like neon signs in a celestial city. These molecules are scattered throughout the galaxy, but in this nebula, they're arranged in a way that amplifies their glow, creating that distinctive reddish hue. Even stranger, Hubble Space Telescope images revealed a ladder-like series of rungs within the nebula, regularly spaced knots of dust that look like steps climbing into space. No one knows what causes this eerie periodicity, but it hints at rhythmic pulses of material being ejected by the dying stars like clockwork. Could the red rectangle be showing us a preview of our own sun's fate? In a few billion years, when our star exhausts its fuel, it too will shed its outer layers, forming a planetary nebula. But will it resemble this geometric marvel, or will it follow the more common, asymmetrical path? The answer might lie in the unseen dynamics of the binary system at the nebula's core. If one star is subtly influencing the other's death throes, it could explain the precision of the structure, a celestial dance where one partner leads the other into symmetry. What makes the red rectangle so mesmerizing isn't just its beauty, but the way it challenges our assumptions about how stars die. Nature tends to favor chaos over order. Yet here, in the depths of space, we've found an exception, a cosmic masterpiece painted with mathematical precision. Whether it's the work of hidden forces, a rare stellar partnership, or some undiscovered physics, this nebula stands as a quiet rebuke to our expectations. And until we unravel its secrets, it will keep glowing in the void, a red geometric enigma, whispering that the universe's rulebook might have chapters we haven't even opened yet. The galactic center excess is like a cosmic flare gun going off at the heart of our galaxy, a burst of gamma rays so persistent, so puzzling, it's kept astrophysicists locked in debate for over a decade. Imagine pointing a telescope toward the Milky Way's core, expecting to see the usual suspects: supernova remnants, pulsars, black holes, only to find an unexplained glow of high-energy light that shouldn't be there. First detected by NASA's Fermi Gamma Ray Space Telescope in 2009, this excess radiation forms a hazy halo around the galactic center, stretching thousands of light years in every direction. The problem: none of the usual astrophysical sources can fully account for it. One camp argues this could be the smoking gun for dark matter, the elusive substance thought to make up 85% of the universe's mass. According to this theory, when dark matter particles collide, they might annihilate each other in bursts of gamma rays, leaving behind this eerie glow. The galactic center, packed with dark matter, would be the perfect place for such collisions, but here's the catch: the signal's distribution doesn't quite match what most dark matter models predict. It's too smooth, too spread out, as if the particles are behaving in ways we haven't anticipated. Then there's the pulsar possibility. The Milky Way's core is teeming with these rapidly spinning neutron stars, which emit gamma rays like cosmic lighthouses. Could thousands of faint, undiscovered pulsars be collectively mimicking the excess? Some simulations suggest yes, but there's a hitch. We'd expect to see more variability in the signal, flickers and pulses that just aren't there. The glow remains stubbornly steady, like a light left on in an empty room. Complicating matters further is the role of cosmic rays slamming into gas clouds near the galactic center. These collisions can produce gamma rays too, but calculations show they'd need to be far more energetic than observed to explain the excess. It's as if the universe is giving us a jigsaw puzzle where half the pieces belong to a different box. What makes this mystery so tantalizing is the stakes. If the excess is dark matter, it could finally crack open one of physics' greatest enigmas. If it's pulsars, it means our galaxy's core is even more crowded with exotic objects than we imagined. And if it's neither, well, that's when things get really interesting. Some theorists have floated wilder ideas: primordial black holes, exotic particle interactions, even remnants of a long-dead galaxy consumed by our own. For now, the debate rages on, fueled by ever more precise data from Fermi and newer telescopes. Every observation tightens the constraints, yet the signal refuses to yield its secrets. Whether it's a whisper from the dark universe or a chorus of unseen stellar remnants, the galactic center excess reminds us that even our own backyard, the heart of the Milky Way, holds mysteries profound enough to rewrite the textbooks. And until we solve it, that unexplained glow will keep burning, a silent beacon in the dark. The KBC Void isn't just another empty patch of space, it's our galactic neighborhood's best-kept secret, and it turns out we're living in one of the universe's loneliest suburbs. While most of the cosmos clusters into dense filaments and superclusters, the Milky Way sits inside a staggering cosmic bubble roughly 2 billion light-years wide, where galaxies are fewer and farther between than almost anywhere else. Named after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who mapped its boundaries in 2013, this void isn't just a curiosity. It's a direct challenge to our understanding of how matter organizes itself across the universe. What makes the KBC Void so startling is the sheer scale of its emptiness. Imagine a sponge where most of the holes are tiny, but one gap stretches across half the sponge's length. That's our place in the cosmic web. Surveys show the local universe around us has about half the galaxy density of the average region. a discrepancy that shouldn't exist if matter were distributed as uniformly as theories suggest. Even more puzzling, we're right at the center of it. The odds of such a perfect alignment are astronomically low, raising eyebrows about whether we're seeing a statistical fluke or a clue to something deeper. One radical theory suggests the void might be the aftermath of a colossal collision, not between galaxies but between universes. If our cosmos once brushed against another in the multiverse, the gravitational recoil could have sent matter rushing outward, leaving behind this hollowed-out region like a tidal scar. Others propose it's evidence of an ancient imbalance in dark energy, the mysterious force accelerating the universe's expansion. Perhaps pockets of stronger or weaker dark energy cleared out our corner of space like an invisible cosmic broom. Then there's the unsettling implication for cosmology itself. If the KBC Void is real and not just a measurement error, it could mean we've been underestimating the universe's lumpiness. That would throw a wrench into calculations based on the cosmological principle, the assumption that matter is evenly distributed on large scales. Suddenly, key pillars of modern astronomy, like estimates of dark energy's strength or the universe's expansion rate, might need rechecking. But not everyone's convinced the void exists at all. Some researchers argue that galactic surveys are inherently biased. After all, it's harder to spot dimmer galaxies at vast distances, which could make our local universe appear emptier than it really is. Others point to the Milky Way's own disk of gas and dust, which blocks our view of certain regions, potentially skewing the data. Even the void's proposed size fluctuates depending on how scientists define its edges, leaving room for doubt. Yet the more we study it, the harder the KBC Void is to ignore. Peculiar patterns emerge when you look closely. Nearby galaxies seem to flow away from the void's center as if repelled by its emptiness, a motion that doesn't quite match standard models of cosmic expansion. And if the void is real, its existence might solve another puzzle. Why measurements of the Hubble constant, the universe's expansion rate, disagree depending on the method used. Living in a void could mean we're seeing a locally skewed version of the cosmos, like trying to gauge ocean currents from inside a whirlpool. Whether it's a true cosmic anomaly or a trick of perspective, the KBC Void forces us to confront an uncomfortable truth. We might not be typical observers of the universe. Our corner of space could be the exception, not the rule, a quiet backwater in a bustling cosmic metropolis. And until we peer deeper into the void's depths or find a way to test these wild theories, we're left with a humbling reminder that sometimes the most profound mysteries aren't out there in the distant cosmos. They're right where we live. The unicorn isn't a mythical creature, it's a cosmic oddity hiding in plain sight, and it's rewriting the rules of how black holes are born. Tucked away just 1,500 light-years from Earth in the constellation Monoceros, this mysterious object weighs in at just 3 times the mass of our Sun, making it one of the smallest black hole candidates ever discovered. That might not sound tiny, but in the world of stellar remnants, it's downright petite, so small, in fact, that it shouldn't exist according to conventional physics. Most black holes form when massive stars collapse, leaving behind cores heavier than 5 solar masses. The unicorn, though, dances on the edge of impossibility, challenging everything we thought we knew about how stars die. What makes this object so baffling is the way it was found. Unlike typical black holes that reveal themselves by devouring nearby gas or warping space-time around visible companions, the unicorn betrayed its presence through subtle tugs on a neighboring red giant star. Astronomers noticed the giant's light oscillating rhythmically, as if an invisible partner were pulling it in a slow, gravitational waltz. After ruling out other explanations like star spots or the star's own pulsations, The only plausible culprit was a compact object too small to be a neutron star, yet too massive to fit neatly into the black hole playbook. Theories about its origins range from the explosive to the exotic. Some suggest it could be the remnant of a failed supernova, where a dying star didn't quite muster the energy for a full-blown explosion, quietly collapsing instead into this lightweight anomaly. Others propose it might have shed much of its mass before collapsing, perhaps stripped away by a binary partner in a stellar tug-of-war. Then there's the wild card. Could it be a primordial black hole, forged in the chaos of the early universe rather than from a dying star? These ancient relics, predicted but never confirmed, would solve more than one cosmic mystery if they exist, but the unicorn's true significance lies beyond its size. If confirmed, it hints at an entire population of overlooked black holes lurking in our galactic backyard, too faint and quiet to detect through traditional means. That would mean our census of these dark objects, critical for understanding the universe's structure and evolution, is woefully incomplete. Even more tantalizing is the possibility that the unicorn represents a missing link between neutron stars and black holes, a shadowy realm where the rules of stellar collapse blur. For now, astronomers are racing to gather more data, scrutinizing the red giant's wobbles for additional clues. Every flicker of light, every shift in spectral lines could hold the key to unlocking this puzzle. Whether it's a cosmic fluke or the first of many, the unicorn reminds us that even the smallest enigmas can force the biggest revolutions in science. And until we crack its code, it stands as a silent challenge. If black holes can come this small, what else have we been missing? Betelgeuse has always been a star that demands attention, a fiery red beacon in Orion's shoulder, so massive that if it replaced our sun, it would swallow Mercury, Venus, and Earth whole. But in late 2019, this cosmic titan did something extraordinary. It began fading. Not just a slight flicker, but a dramatic dimming that saw it lose nearly 2/3 of its usual brightness in a matter of months. For the first time in recorded history, one of the night sky's brightest stars seemed to be vanishing before our eyes, and the astronomical community held its breath. Was this the prelude to a supernova, the star's final act before exploding in a blaze of glory? Theories flew fast and furious. Some speculated Betelgeuse was on the verge of collapse, its core running out of fuel after millions of years of fusion. A supernova that close, just 650 light-years away, would be a once-in-a-civilization event, visible even in daylight and outshining the moon for weeks. But as telescopes like Hubble and the European Southern Observatory's Very Large Telescope trained their lenses on the star, a different picture emerged. Instead of the telltale signs of an impending explosion, they found something almost mundane: dust, lots of it, a colossal cloud of silicate and carbon grains ejected from the star's surface, had drifted between Betelgeuse and Earth, acting like a cosmic veil. But here's the mystery: dust doesn't just appear out of nowhere. Something had to kickstart this sudden ejection. One leading idea points to a colossal belch of gas from the star's churning interior. Red supergiants like Betelgeuse are notoriously unstable, their surfaces bubbling with convection cells the size of solar systems. If one of these cells erupted, it could have flung a surge of material into space, where it cooled and condensed into dust. Supporting this, astronomers spotted a massive hotspot on Betelgeuse's southern hemisphere just before the dimming began, as if a stellar geyser had burst forth. Yet not everyone's convinced. Some researchers argue the dust explanation is too neat, that the timing and scale of the dimming don't fully match what we'd expect from a simple dust cloud. Could there have been a more violent event, a partial collapse, or even a swallowed companion star that triggered the outburst? Others wonder if Betelgeuse's dimming was a combination of factors: dust and a natural dip in the star's brightness as it pulses through its regular cycles. After all, Betelgeuse is a variable star, its luminosity waxing and waning over years. But the 2019 event was far more extreme than anything in its recorded history. What makes this episode so fascinating isn't just the science, it's the reminder that even the most familiar stars can still surprise us. Betelgeuse has been a constant in human skies for millennia, yet in a cosmic blink, it showed us how dynamic and unpredictable the universe really is. And while the star has since regained much of its brightness, the questions linger. Was this a one-off event or a sign of deeper instability? Could the next dimming spell disaster? Every new observation adds another piece to the puzzle, but Betelgeuse keeps its secrets close. For now, all we can do is watch, wait, and marvel at the fact that we're witnessing, in real time, the slow-motion drama of a star that might one day rewrite the night sky. The Hubble Tension isn't just a scientific disagreement, it's a full-blown cosmic identity crisis, forcing astronomers to question whether we've misunderstood the universe's most fundamental behavior. Picture two teams of scientists measuring the speed of a car, one using radar and the other timing it between mile markers, only to get wildly different results. That's essentially what's happening with the expansion rate of the universe, known as the Hubble constant. For decades, we've had two primary ways to calculate this number: by studying the cosmic microwave background, the afterglow of the Big Bang, and by observing pulsating stars called Cepheids in nearby galaxies. The problem: these methods stubbornly refuse to agree, with the discrepancy now reaching a confidence level of 5 sigma, the gold standard for a genuine scientific conflict. At the heart of the tension lies a gap of about 7 kilometers per second per megaparsec. That might sound trivial, but in cosmology, it's a chasm. The Cepheid route, calibrated by the Hubble Space Telescope and later refined by Gaia's stellar surveys, suggests the universe is expanding at roughly 73 kilometers per second per megaparsec. Meanwhile, measurements of the cosmic microwave background by the Planck satellite, assuming our standard model of cosmology is correct, peg the number closer to 67. This isn't just a rounding error, it's a rift that threatens to crack open our understanding of cosmic history. One camp argues the discrepancy stems from unaccounted-for quirks in our measurements. Could Cepheids, those cosmic yardsticks, be tricking us? Their pulsation periods are tied to their brightness, which lets us gauge distances. But what if dust or metallicity skews the readings? Others scrutinize Planck's data, wondering if subtle biases in how we interpret the microwave background's faint whispers might be to blame. Yet after years of cross-checking, neither side has found a smoking gun. The numbers hold firm, deepening the mystery. That's when the conversation turns radical. If the tools aren't flawed, perhaps the universe itself is. Some theorists propose dark energy, the mysterious force accelerating cosmic expansion isn't constant, as we've assumed, but evolving over time, stronger in the modern era than in the early universe. Others speculate about early dark energy, a burst of repulsive gravity that briefly surged during the cosmos's infancy, leaving fingerprints Planck might have missed. Then there's the wild card. What if dark matter interacts with itself or ordinary matter in ways we haven't modeled, subtly altering the expansion rate? The stakes couldn't be higher. If new physics is required to resolve the Hubble tension, it would rank among the most profound discoveries since Einstein's relativity. Already, telescopes like JWST are diving into the debate, scrutinizing Cepheids and another class of distance markers called red giant stars with unprecedented precision. Meanwhile, next-generation cosmic microwave experiments, like the Simons Observatory, aim to re-examine the early universe's blueprint with finer detail. What makes this clash so electrifying isn't just the scientific upheaval it promises, it's the humility it imposes. For all our advancements, the universe might still be holding back its deepest secrets, teasing us with contradictions that defy easy resolution. Whether the answer lies in overlooked errors, exotic particles, or a cosmic paradigm shift, the Hubble tension reminds us that even the most bedrock truths of astronomy are open to revision. And until we bridge this gap, every new measurement carries the weight of potentially rewriting the story of everything. The cosmic web is supposed to be the universe's grand architectural blueprint, a vast, intricate network of gas filaments weaving galaxies together like threads in a tapestry. Simulations have painted this picture for decades. After the Big Bang, dark matter's gravitational pull sculpted ordinary matter into a sprawling web, with dense knots where galaxies cluster and shimmering strands connecting them across the void. But when astronomers set out to map these threads, they hit a wall. We've only spotted a fraction of the filaments that should exist, leaving a glaring gap between theory and observation. It's as if we're trying to study a city's road system by only seeing the intersections, with most highways mysteriously invisible. So where are all the missing filaments? One possibility is that they're simply too faint for our current telescopes to detect. These threads are made of diffuse, ionized gas, so thin and hot that they emit almost no visible light. Instead, they reveal themselves indirectly, like shadows on a cosmic curtain. When light from distant quasars passes through the filaments, certain wavelengths get absorbed, leaving telltale fingerprints in the quasar's spectrum. This method has confirmed some filaments, but it's like using a flashlight to trace a spiderweb in the dark. You only see the strands the beam happens to hit. Another clue comes from the gas's temperature. Models suggest filaments should exist in a range of thermal states, from warm to screamingly hot. The warmer ones have been easier to spot, but the hottest, those heated to millions of degrees by shock waves from collapsing galaxy clusters, might be emitting mostly in X-rays, a wavelength range we've only recently begun to explore with sufficient sensitivity. Telescopes like ESA's Athena and NASA's Lynx, slated for launch in the coming decades, could finally unveil these hidden rivers of plasma. Then there's the dark matter factor. The cosmic web structure is dictated by dark matter's gravitational scaffolding, but the relationship between dark and ordinary matter in these filaments isn't fully understood. Could some filaments be dark, dominated by matter that doesn't interact with light at all? Or might magnetic fields threading through the web be shaping the gas in ways we haven't accounted for, making it clumpier or more elusive than simulations predict? The stakes are higher than just filling in a cosmic map. These filaments aren't passive threads, they're the universe's supply lines, funneling gas into galaxies and fueling star formation. If we're missing half the network, we're missing key clues about how galaxies grow and evolve. Some researchers even speculate that the missing filaments could be hiding pockets of primordial gas, pristine material untouched since the Big Bang, a cosmic time capsule waiting to be discovered. What makes this mystery so tantalizing is that the answer might already be in our hands, hidden in existing data. Advanced algorithms are now sifting through observations from telescopes like the Hubble and the Very Large Telescope, searching for subtle patterns that could betray the filament's presence. Other teams are using gravitational lensing, where massive galaxy clusters bend light like a magnifying glass, to hunt for distortions caused by these ethereal strands. Every new detection chips away at the enigma, but the full picture remains frustratingly out of reach. Whether the filaments are fainter, hotter, or stranger than we thought, their absence is a silent challenge to our models of cosmic structure. And as telescopes grow more powerful, we might soon find that the cosmic web isn't missing at all, we've just been looking for it in the wrong light. Until then, these ghostly threads remind us that even the universe's grandest designs can stay hidden in plain sight. From mysterious signals to invisible forces, these 20 cosmic puzzles are more than just scientific curiosities. They're humbling reminders that the universe operates on a scale we're only beginning to comprehend. Think about it. Every time we solve one cosmic riddle, another takes its place, deeper and more bewildering than the last. The wow signal's fleeting whisper, the dark flow's inexplicable tug, the Great Attractor's hidden pull, these aren't just gaps in our knowledge. They're invitations to dig deeper, to question bigger, and to rethink what's possible. What's truly remarkable isn't just the mysteries themselves, but how they shape the future of discovery. Tabby's star's erratic dimming forced us to build better telescopes. The Pioneer Anomaly's tiny drift sparked debates about the very laws of physics. Even Oumuamua's bizarre acceleration sent researchers scrambling to design missions that could one day chase down the next interstellar visitor. These aren't dead ends, they're launch pads. Every unexplained flicker or gravitational oddity pushes scientists to innovate, to peer further, to imagine wilder solutions. And let's not forget the human side of this quest. Behind every dataset, every conflicting measurement, are people, astronomers lying awake at night running calculations, engineers tweaking instruments to catch a whisper of signal, theorists scribbling equations that might just crack the code. That's the beating heart of science, not certainty but curiosity, the willingness to say we don't know yet and then pour a lifetime into chasing answers. So here's the real question: which of these cosmic head-scratchers keeps you up at night? Is it the eerie silence of the Fermi Paradox or the Black Knight's orbital legends? Maybe the Red Rectangle's geometric perfection or Betelgeuse's dramatic dimming act? Drop your pick in the comments. We're all part of this conversation. And if you're hungry for more deep dives into the universe's greatest mysteries, hit subscribe and ring that bell. The cosmos isn't done surprising us, and neither are we. Keep looking up, stay wonderstruck, and remember, the next big discovery might be hiding in plain sight, waiting for someone sharp enough to connect the dots. The universe is vast, uncharted, and utterly unpredictable, and honestly, that's the best part.